Very good morning, friends. Today's subject of discussion is microwave assisted organic synthesis. This is the synthesis of organic compound with the assistance of microwaves. It is abbreviated as MAOS. This is a microwave synthesizer from SEM Discover. Here we know that green chemistry is a process or a philosophy in which we achieve the sustainability of earth by reducing the pollution, which can be in turn achieved by the lesser usage or stoppage of production of waste materials or usage of less hazardous material and generation of less hazardous material. Along with this, another way of achieving greener synthesis is the effective utilization of the energy. Microwave assisted synthesis is an answer to that. What are these microwaves? The microwaves range in their wavelength from zero point 0.3 millimeter to zero point 0.5 meters. The wavelength of these microwaves is in between the infrared rays and the radio waves. Its frequency lies between 1 into 10 power 12 to 6 into 10 power 8 hertz. In general, the lab microwave equipment which we use gives or produces the microwaves with a wavelength of 12.2 centimeters and which can give the energy of around 2.45 gigahertz. This has been chosen with the intention of overcoming with its interference with telecommunication and the radar equipments. Microwaves woven discovery is by accident. Its discovery goes back to 1946. An American engineer, Percy Lee Baron Spencer, working for Raytheon, was testing the magnetron, a new type of vacuum tube at that time. Accidentally, when he leant against the magnetron, the candy which he had kept in his pocket started melting. This observation led to further keep the kernels in front of the opening of the magnetron, and this bounced as popcorns all around the room. When eggs are kept in front of the magnetron, waves produced by the magnetron, the eggs exploded. Yes, there is something in this that the enormous of energy is produced in the form of heat. With this invention, Raytheon first produced the microwave and they named it as radar ranges. This equipment was very big in size and very expensive, which a common man could not afford. Later, in the year 1967, Amana, the subsidiary of the Raytheon, produced the first microwave oven for domestic use. Until mid 1980s, microwave ovens are used for only cooking purpose. That is just heating purpose. In 1986, Richard Gedia et al. From Laurentian University of Canada and Magitich et al. From Georgia University of United States of America, they transitioned this micro oven for cooking purpose to laboratory purpose. Now, in the laboratory, we use microwave ovens. These microwave ovens accelerates the reaction enormously, and thus the energy efficiency has been produced, which is the one of the aims of green chemistry synthesis. The domestic microwave oven construction is like this. It has a magnetron which comprises of heated cathode and an anode. When the electricity is passed, it produces the microwaves and that passes through the halo tube which has reflective walls, and it guides the microwaves produced into the microwave cavity. This microwave cavity is made up of reflective walls, and there is a mode stirrer which rotates. The purpose of this mode stirrer is to equally distribute the microwaves that enter into the cavity throughout the cavity. It has a turnable table onto which we can keep a microwave transparent vessel, and when it is rotates, there is equal distribution of heat to all over the particles or the components present in the vessel. Microwave's beauty is that it is transparent to PTFE, paper, glass, but at the same time it is heating only the molecules or the particles or the components but without heating the vessels. There are two types of microwave reactors available now in the market. The first one is the monomode reactor, which is especially used for carrying out the reaction. What is this monomode? This monomode microwave reactor generates the focused waves into the cavity reaction cavities in which the reaction vessel is kept. This utilizes optical fiber or IR detector. The beauty of this monomode microwave reactor is that the reaction vessel is made up of Teflon and it can withstand the pressure of around 1500 pounds per square inch gauge. It can also withstand enormous amount of temperature which is generated. By this monomode microwave reactors, the temperature and the pressure can be controlled. That's why there is homogeneous heating. In case of the multi-mode reactors, which we have shown here in this figure, which is used for cooking purpose, there is No homogeneous heating. Some spots will be at hot condition, some spots will be cold condition, because there is no homogeneity of microwaves. Thus, the temperature or the pressure cannot be controlled. Hence, monomode type of microwave reactors are more useful for reproducible results in the laboratory. How these microwaves heat? What's the mechanism behind it? It follows different mechanism. One of the mechanisms is dipolar polarization mechanism. The dipolar molecules, when they are in the electric oscillating electric field, they try to align with the parallel to the electric field. In the absence of the electric field, they are haphazardly distributed, highly disordered, entropy is very high, and thus way energy is less. The positive end and the negative end. It gives a dipolar molecule. A molecule which has the positive and the negative end is a dipolar molecule or a polar molecule in brief. When an electric field is applied, the molecules which are haphazardly distributed try to align across the magnetic field, the negative ends facing towards the positive center and the positive ends facing towards the negative center. When the electric field is oscillated, we change the electric field. This try to oscillate once in this phase, another in this phase. Alternating electric field, they oscillate. When they oscillate, they collide with the other particles and it increases their potential energy. And this potential energy is converted into kinetic energy and it gives rise to thermal energy. The process of converting electrochemical energy to heat energy. Here, the it is given as tan delta is equal to epsilon bar epsilon dash. Delta is the dissipation factor, epsilon is the dielectric loss, and epsilon dash is the dielectric constant. This is not only the mechanism, there are additional effects, other mechanisms which we find by in heating by microwaves. The additional effect along with this dipolar polarization effect is interfacial polarization. This is also called as space charge polarization, or it is also named as Maxwell Wagner effect, which is given by named after the scientists who explained this effect for the first time. When the molecules are there, the ions are there, or the dipolar molecules are there in ionic liquids, the ions are there, they are distributed unequally in the absence of an electric field. It is shown in this part A of the figure. This is the material in the absence of the electric field. They are haphazardly or randomly distributed. When we apply electric field across the two and cathode and anode, The negatively charged ions moves towards the positive center, and the positive ions moves towards the negative electrode. And when they move, when they have different types of material, at a particular junction, interfaces are formed. They move to that a certain extent. Beyond that, they won't move as interfaces are formed. When there is the accumulation of charges, and this accumulation of charge is called as space charge. These charges, in the presence of this electric field, they align along with the magnetic field or against the magnetic field, and they rotate and they create their own electric field. And because of the interaction of the electric field, there is interfacial polarization, and this gives rise to collision, and this collision results in the thermal energy. This type of interfacial polarization is seen in heating effect when the conducting particles are in contact with non-conducting medium. Another effect which we see, another mechanism which the microwaves convert the electrochemical energy to heat energy is by rotational energy. The rotating molecules, they grab the microwave energy, and they, because of they took that microwave energy, there increases the rotational energy. Here, if there is the polar molecule in the presence of the microwave energy, alternating electric field gives alternating microwave this thing, and they rotate. Once like this, another they move up, again come down, again move up, and this rotational energy gets accumulated, and this appears as heat in the polar molecule. Microwave frequency, when it equals to that of the molecular rotational frequency, electric field interacts with the molecular dipoles, and thus it increases the rotational energy, and that is dissipated as heat energy. There are three mechanisms by which the microwaves heat the molecules. One is dipolar polarization, second is interfacial polarization, third is rotational polarization. And there are also another mechanism, there is ionic conduction mechanism. In the solution, when it is having ions, under the influence of microwaves with the alternating electric field, that increases the collision between the ions, and it gives rise to kinetic energy, which is dissipated as heat energy, as we have shown this in interfacial polarization. These are the three mechanisms by which the microwave generates heat energy. In the next presentation, we will deal with other aspects of this microwave reactions. The types of solvents we use. What types of solvents are more suitable? What are the limitations? What are its advantages? All those things will be the subject of discussion in the coming presentation. Till then, have a nice day. Thank you.